It's recording. Start when you're ready.
Hello, we're Team 772 from Hartsville, South Carolina, and this is our explanation of our world's robot. I'm Griffin.
I'm Maverick.
So to start with, for our drivetrain, we did a parallel plate drivetrain in the beginning of the season. We used a Go Build a Drive because we're a 2-year, junior, senior only school, so we wanted the new juniors to learn. But towards states, we switched to this custom drivetrain because we figured it was just the next step. We did we catted everything in Onshape. We really wanted to make our actual parallel plates super small and compact because we wanted to be a small robot so we could move around on the field super easily. Albert, can you talk about the odom?
Yeah, so as of now, we use this 4-bar odometry pods, which is not what we used for the majority of the season. We started off by using custom odometry pods, using a board from a company called Opti, but we realized that those odometry pods were too precise for our rev control hubs to handle. So what we needed to do is we needed to downgrade to these odometry pods, because if we didn't, we would have really choppy autonomous paths because the control hub wouldn't be able to capture every single every single packet that this sends. So through that we upped our consistency a lot, and we were able to get faster autos.
So we have four 435 RPM motors, and they're belted 1-to-1 for the wheels, and we use the new Go Build a traction wheels so that we can they're bigger than the old ones, and they also just have more traction in general. We also use a servo hub because a big issue that we had towards the beginning of the season was that our everything would just die when we used it all at once. So we didn't really want to have our servos just randomly dying, so we got the servo hub, and it's been pretty helpful so far.
The idea behind the servo hub is that it provides more consistent power to every single servo at once, so we don't have that issue with too much power.
We also use pinpoint, I think what Albert mentioned, but we use pinpoint in combination with these two. In the beginning of the season, we used 3-wheel, but pinpoint has just been a lot more reliable for us.
Because it uses that internal gyroscope inside of it, we're able to get a much more accurate sense of what the robot's heading is.
This part's just kind of cool, but we have these side plates, these Lexan side plates that we attached. All these are 3D printed, so we have these 3D printed license plate or alliance marker holders. So we just put it on the inside, and then in the spots that there's holes in the pockets, we put screws through. So that allows us to just slip in and out our alliance marker in between matches. Our vertical slides have changed a lot throughout the season. In the beginning, we used the Viper slides from Go Builda, but we switched to Misumis because they're lighter. We used this 300-pound test line, but a big issue that we had was that we kept on having too much tension in the string. So every single time that we would go up, by the time that it would try to pull down, one string would be completely loose, and that's because there wasn't really a rerouter. So last minute, we were struggling for time before states, so we added this Baron rerouter right here, and basically what it does is it moves the string from this one right here, which makes it go up, and it adds a kind of just pulley system inside of it so that it's completely parallel with the vertical slides. And by making it parallel, we reduce the amount that it actually we reduce the amount it's super tight at the bottom, and that helped us a lot in not overheating our motors at all, because it doesn't have to pull down a ton instead of it doesn't have to fight itself. And then for our outtake, we actually got this tip from 5064 Aperture Science. But one thing that we did is that we used on these springs, we wanted to have a little bit of movement, but the problem is you can't climb on springs. So we use our vertical slides to climb. So we have this kind of system that's an elastic pulley. So there's a string here, and it connects the two. And it's shorter than it's longer than the actual spring, so that the spring can move in and out a little bit. But it's not so long that the spring is going to stretch a ton. And then whenever we need to climb, we just climb, and it pulls the string. It pulls the string, but not the spring.
One thing that I'd like to point out about this climb system is that unlike most people that use a PTO, we rather use three 1150 RPM motors that are all connected to a gear ratio that gears it up. So through this, we still have that speed that we need to go up and down quickly, but we also have that extra torque that we need to go when we climb. And the reason we decided to do this is because we prefer simplicity. Rather than most teams that have that complex PTO system that harnesses the power that the drivetrain gives you at the end, oftentimes what we notice is that it can break and it has too many moving parts. So instead we just opted for a 3-motor design, which gives us that speed, but it also gives that torque that we need at the end. One other thing that I'd like to mention is that we use a absolute encoder here rather than the default motor encoders so that we can get a better understanding of where the axle is compared to just reading the values at the motor scale.
All right, so that's most of like our vertical ascension, our drivetrain. The next big part of our robot is the actual picking up system. We went through a lot of designs throughout the season. We ended up landing on claw to claw because we found that it's the most reliable. So we have sets of horizontal Misumi slides. They're a little bit longer than they need to be, but we weren't sure how long it was going to end up being. We have these two linkages. We originally had them out of 3 printed parts, but we switched them to Lexan because our 3D printers couldn't physically print large enough linkages that would like fit to what we needed. So we cut them out of Lexan, and they're lighter and they're just like more durable. Like we can bend these a ton and they won't get hurt at all. We haven't like had any issues with that at all.
Another thing you might notice is these slides seem a lot longer than they actually are. And the reason this is because we originally wanted to belt these or string them. But we realized that we don't actually need all that extension, and the amount of extension that we get just by extending out like this is perfectly fine for what we need. So rather than stringing it and adding a lot more complexity to the robot, we just decided to go and add those linkages.
Yeah, like you said, we wanted to string it, but by the time that we were like, it might be better to string it than to do linkages, we would have to design like a whole new subsystem that would allow us to route string to our slides, and we just didn't have the time to do that like in between competitions. So we decided to just stick with our original design, and overall it's worked pretty well. Stringing might have been a little bit better because it makes it easier to grab from over here, like under the first rung, but other than that, we haven't really had any issues with it. So for our actual intake system, we use a lot of servos. So we have these 2 Axon Minis that pivot the actual main system. We gear them because we didn't want to have a lot of stress on the servos themselves. On our last design, we just did direct drive, and it wasn't great. So by just gearing them, we've had like way more success. We gear a lot of things on this robot because I think one of our general mottos is like we don't want to put stress on things. So if we're putting a lot of stress on the servos, that's not really effective, and it makes the overall design just worse because things break easier and we have to replace things more often, and we didn't want to do that at all. So then we have 2 stages. So this is the first stage. That's what these 2 minis power, and then our second stage. This mini powers. Again, we have it geared, and then it's a little bit smaller inside. We also have a pivot on here and a actual grabbing claw. So we have a Go Build a super speed servo. We had it a speed and we had a super speed, but we keep on switching it. And we also have a camera.
So on this robot, this camera basically points down and it looks at these samples and figures out what rotation they are at. The way we do this is by using trigonometry. We basically draw a line through this sample and then plot it out on the unit circle. And then depending on where that line intersects on the unit circle, we're able to do some trigonometric mathematics and figure out what angle this is at. The way we do this is by passing it into this fisheye camera right here. And the reason we decided to choose the fisheye was because we thought it would give us a better idea of how many samples there were in the submersible. But what we later on noticed was that this would give us some problems because the pipelines don't really work as well with these fisheye cameras as they do with just normal cameras. So on that pipeline, we run that trigonometric output, and we're basically able to figure out where that sample is and then automatically align our clock to it. I don't think it's working right now.
It's zooming out.
Having a bit of an issue. But anyway.
Yeah, well, Aaron, let's restart the code real quick.
Oh, okay.
We're just going to restart the code real quick so we can actually show it.
Got it.
No, it's alright, you can cut it. Like at one part.
Right. I don't know why it's not working.
It's fine. All right, so there we go.
Cool. Okay.
So,
All right, we got it.
All right.
as I was saying, on that servo, it's able to basically figure out exactly where it is, and even if you have, maybe a second one in there, it's still able to sort of null that one out and still just pay attention on the actual, sample that we need. And the way we do this is through a process called watershedding, where we basically look at each of these samples and we figure out if there are any intersections between where they get very close. And through those intersections, we're able to basically differentiate between each sample. So we do that with a mix of that watershedding algorithm, and we also just do color detection to detect which sample we want.
So we actually have two versions of our code. We have a version for blue and a version for red. So in between auto and teleop, our primary driver, he clicks a button either right or left, and that determines which color we are, and that's how we choose if we're grabbing reds or grabbing blues. And we haven't had any issue with that so far. There hasn't been any errors, so we just do it in between and it works great. For the actual grabbing, so once it's pretty fast at pivoting and it updates pretty regularly. So we come down and we can just know that it's gonna come down right there, and then we grab it and then we can do the transfer system. But if for some reason it doesn't work, what we can do is we have R1 and L1 on our controller. It rotates it, so if we hold it down, it'll manually rotate it. So if for some reason we have to override it, we still can because the camera turns off when it's down. So that's also an issue that we were having, was that sometimes when it was down, it would still be rotating and it'd still be trying to detect things. And I think that the override helps a ton with that.
So that automatic cutoff just helps differentiate between what the actual driver is doing and what the robot's doing, so we can have that balance.
So looking at the actual transfer sequence, we grab it here and it's pretty fast. So, all right. So essentially what it's doing is once we have a sample in our intake system, we bring it back to here, and if it's up here, the claw is loose enough so that when it hits back, all of the momentum will be transferred to the sample, and it'll want to slide down naturally. And when it slides down, we have this claw, which just goes directly down, hits it, and as soon as it hits it, we use this button to determine if it's inside, and if it is inside, it immediately closes and then transfers back.
And while this button helps us on this, it also helps with our autonomous and scoring specimen, which we'll talk about a little bit later.
Yeah, I do want to talk about the button a little bit, like how it works mechanically. So basically, hold up, I don't know the best way to show this, but we have a limit switch inside of here. So it's a very intricate claw. It's super small. There's a lot of fine details to it, but you can kind of see inside of there. There's the limit switch, and this button is just a piece of plastic that we printed, and whenever it's pressed down, it makes a sound. You can hear that sound. That's the limit switch actually being pressed. So it doesn't matter if it's pressed over here or over here. It'll work the exact same anyway. And that's been really helpful in making the transfer even faster, because that's also an issue that we were having. We wanted the cycle time to be faster, and a big part of that is making sure the transfer always works.
What this also does is it adds a lot of consistency. Beforehand, when we used our bigger claw, we didn't have that switch on there, and what would happen is it would press down, and it wouldn't actually know if it was there. So we would have this delay that we'd have to hard code in, but it wouldn't always be accurate, and a lot of the times we wouldn't know if the sample was there. So when it comes down, if the sample wasn't actually there, or if it was sitting in a way that wasn't exactly great, we would have a lot of failures.
Yeah. A big thing with our failures, so sometimes what would happen, we really haven't had it happen with this, with our Worlds robot, but what happened before was that we were worried that these samples, if the transfer fails, the samples fall into the robot, and since you can only possess one, you're cooked for the rest of the match. So we added this cover right here, which the Goat Viome designed. It's very intricate. It's shaped kind of like a little cradle, I guess. I don't know. but it covers up the battery as well, and it makes everything like fit really nicely. We haven't really showed this yet, so we can. Everything on this robot is super packaged because we wanted to keep our weight low to the ground because we were worried about like if we would tip when we have our vertical slides up. So our battery's in the front. We have our 4 motors kind of in the middle, and then the other 3 motors are in the back. Our center of gravity on this robot is really, really good. I would say it's probably like around like the center here. We do have a lot of weight added from the entire vertical subsystem, but a lot of that is counteracted by the intake and also having the battery and the motors here.
Through this, we take a lot of inspiration from competitions like the first robotics competition where weight class does matter a lot. So we try and sort of keep all of our weight in one place and keep our robot as light as possible, because even if our robot doesn't have a weight limit, it's still able to help us sort of know where we're at and make sure that this robot's in a good position.
All right, so talk about the outtake a little bit. This went through a lot of designs. We landed on this one. It's made of aluminum primarily because we had it plastic before. Even though it was lighter though, it kept on breaking, and it like whenever it would snap, that would just add so much more time. And we also figured that metal would just be more consistent, so we tried it and it's worked great so far, I'd say. One thing that we did learn though, so like we had our own CNC, like we have a at-home CNC that we have like in our school. So we custom made all of the parts on this robot, and that was a really, really big process. But one thing that we learned a lot is that we have a lot of slop kind of. So if you look in here, there's kind of a little bit of wiggle in here, and the main reason is because the bearings aren't exactly 14 millimeters wide. We didn't realize that at the time because this is our first year CNCing things, but that allows the bearings to wiggle back and forth a tiny, tiny bit, but it's noticeable and it causes a little bit of error in competition. So that's something that we noticed, especially during Worlds, and we wanted a lot of precision. We're gonna fix that next year, make sure that we test a lot of things, but it's just something that we noticed throughout the season.
Yeah, one team basically taught us that to get that figured out, you have to print out, or you have to cut out a plate with different tolerances, and then we'll basically stick a bearing in and figure out which works best.
We have another 2-axis, like a 3-axis arm on here. 1, 2, 3, right? Again, we use gears everywhere because we want to preserve the longevity of the servos. These are 2 minis. They used to be maxes, but the maxes were just too slow. And also, since they're geared down a tiny bit because we use gears, we really needed that speed because the big issue that we were having was our vertical slides weren't fast enough and our outtake wasn't fast enough. So with this new design, we fixed everything. I don't know if we mentioned earlier, but those 3 motors are 1150 RPM. We did, okay, cool. So basically, this second stage of the outtake system is 3D printed. We don't really need a lot of like structure here because it's not really doing much. The most that it's doing is it's like slamming into the wall when we grab specs, which we can actually talk about a little bit. So,
and then one other thing that I'd like to point out, you might see all these servos on the robot and you might be wondering, do we have issues with that? And the answer is yes, we do. We have a lot of voltage issues with the way that our servos work and how they sort of provide power. And what we've noticed is that if we provide too much power or there's too much strain on a lot of servos, drawing a lot of voltage and amperage from our robot, we'll have issues with them stalling out and sort of just giving out flopping mid-match. So we're still working on issues on that. But what we've been noticing is that using those servo hubs and sort of making sure that everything's in the right place and not pushing against something will definitely increase the amount of servos that you can have on your robot without overdoing that current limit and making it stall.
To add on to what he's saying, like we use like the in Axon, we can lower the amount of maximum power that it's able to use. So a lot of these are set to like what, 50, 60%?
Out of the box?
Or no, like we
right
set
now,
them to,
set to like 6%.
because at their maximum value, these servos don't need that much power. Like a lot of these servos aren't really working that hard, so like we don't need all of that power. And by using it, it's just draining battery. Our battery life is something that we had a huge issue with throughout the season. But I think that we're getting better at it, and we're understanding more how it works directly.
One thing to note is while Axon does ship these pre-tuned for robotics, that they do not tune out that voltage. And it's very hard to find that on the website. We had to search for a while to figure out that information about how the Axons work. So just note that whenever you're using these for robotics use, you want them around 65-70% of their maximum power.
Yeah, you're gonna have to do a lot of tuning with axons. That's something that we noticed is that they're not very friendly, but they work really well a lot of the times. All right, so we're gonna show our specimen scoring. All right, more of our grabbing. So we can just use this outtake arm to grab directly off the wall. So since it has multiple, we just drive forward and then we close the claw and then we click a button and it does an entire sequence where it just puts it up. And then we can go score on the bar really easily. So if you want to go show that. So it does it in like a second. This was a lot faster than what we used to do, which was we would go from below. We had it a little further down. We saw this that like a lot of Romanian teams were doing this, and it's just way faster. And like it scores better than what we could do.
Yeah, the way that we originally did it would have you do around 2 to 3 movements on the robot, and that would be a lot for the driver and button presser to do. So rather than doing it like that, we decided to sort of score it in this sort of pistol sort of sense, where it would score it from above, so that you wouldn't have to do as much work on the driver's end.
You know about how it works on autonomous.
In autonomous? Oh yeah. So while this works in teleop, this same mechanism is being used in auto. But since in autonomous there's a lot more of the thinking being done on the computer, there also needs to be a lot more information being given to the computer. So while we have that odometry, it's not always as precise. So when we come to this wall to grab these specimen, while the odometry pods are going to be there, they're always going to have a little bit of sort of failure, and they're not going to be exactly precise. So another thing that we do is we employ the use of our button over here, also for picking up these specimen. Then when the robot comes up to it during auto, it'll feel that button click, and it will go in and pick up. What is that? Okay, that's all good. Anyway, the idea is when this button will get clicked, it'll automatically go in, it'll close that, and then it'll lift up. The reason we didn't do this in teleop was because we noticed that the human player needs some time in teleop to work with the drive team as well to sort of orient the specimen correctly. So if that presses the button and it automatically closes, then they won't have that time to negotiate. But in autonomous, where the robot is doing all the thinking, this is a great way to remove some of that, or to add some of that consistency to the robot and just make it a little bit better.
Yeah. That's about it. Another thing about like our sample scoring, we kind of do it in a suboptimal way. Our grabbing is really good and our transfer is really good, and it's super fast. But the big issue, like the big difference that we have between a lot of teams is that when we have our grab, I'm gonna do a transfer sequence real quick. So you can see that where it grabs it, it's kind of like below. And a big problem with that is that when the bucket gets kind of full, we kind of have to like hover over the bucket, and this sample pushes some of the other samples around, and we aren't able to, like, we have a much lower maximum than a lot of other teams do. What I think what the optimal strategy would have been to do is to have something like this, which our teammates at Worlds, Gyro Body Droids, they had something kind of like this, where it puts it like this, and then basically you can just like lay it down in the bucket when it gets super full, and that's just a lot more efficient. But it's something that we learned. This season was a lot about like learning like the basics of FTC, and also like how do we go from the level that we were at before to the level that we're at now, and that the learning curve is really different between the two. We've had a lot of like issues with our mentorship, and we have the GOAT Carl. He locked in and he's helped us a lot. So having technical mentors is really important to like getting better as a team overall.
Yeah, one thing to note is that in this last like sort of stage, when you're trying to get to that last 10% and sort of rise up above everybody else to sort of get to those points where you're winning divisions at Worlds and stuff like that, it sort of becomes more of an idea of who you know rather than what you can find on the internet, because there's a lot of small things like the servo issues or the fisheye camera lens that aren't really available on the internet, and you can only get from experienced teams like the ones in Romania who have pioneered this idea of picking up the samples like this, or just having like engineering mentors who are able to provide you with those ideas.
One more thing I want to talk about, which has been kind of big for us this season, it's actually why we lost our qualifiers, is electrical. Electrical isn't super fun. We at the beginning of the season, the reason that we lost our qualifiers is because our electrical got tangled and it limited our maximum extension, and then we couldn't grab for the rest of the match, and we were just kind of cooked. And that happened in the first match, and we were seed number 1. So that wasn't great. But other than that, like, electrical isn't that bad. A big thing though is we switched from the snakeskin to this kind of like wire wrap, I guess. It's kind of made so that it just kind of wraps around the wires, and you can access them at any point in the entire robot. And that is so much more helpful than the snakeskin, because the snakeskin, you have to fully take it off whenever you want to like fix any small issue that comes up. Another recommendation that I would have about like electrical is whenever you connect the servos to extension cords, zip tie them together so that you don't risk them coming unplugged during a match. So we do that everywhere on our robot. Yeah, like for instance here, it's zip tied because we really don't want to risk like it coming unplugged and we aren't able to play the rest of the match.
Yeah, it's just little things like that you always want to be able to pay attention to, because those are always, the things that are going to come back to bite you in the butt. You can always design a very good robot, but if you sort of forget those small things that like electrical and wire management, they'll come back and definitely hit you.
Like electrical is way bigger than you might think it is. It could make or break your team, but you really want to make sure that you're putting your best effort into like making sure that your robot looks good as well, because at a certain point, when a lot of teams are really good, or even like at a similar skill level, what it comes down to is, does your robot look good? And if your robot isn't looking good, teams are going to be less inclined to like want to pick you. I feel like that's kind of something that we've learned, is that that's like a pretty big lesson, is that looks do matter in robotics. So
at least in FTC, I don't know how it is in like VEX or FRC. But
same in VEX.
Same in VEX. All right, cool.
I think that's about it. Thank you.
Yeah, have a good year. We'll see you guys next on the field.
Decode.